All right. Going a little early here. Let me get us all out of here before it starts pouring down rain. So, overall, exams are pretty good. Be kind of what your grade is. I put an announcement on the canvas so you can see what your grade on the exam was, as well as kind of what your current grade in the classes. So I kind of have everything weighted, according to the syllabus. So one thing I'll point out is that if you look on here, and it kind of, you click on your grades in it and look at it, what it kind of shows you is how much each category is weighted. I treated this as though it's going to be your best exam, so I kind of gave it that heaviest weight. If it ends up not being, like, your grade could change quite a bit, if you do better on the second and final, this goes down to, I think in this class it might go down as low as 10%. Right, so if you do better on the next couple exams, if you didn't do too hot in the first one, you can really have kind of a pretty big influence on your grade there. I hand your exams back so you can kind of look at the grading. I'll probably put up the answer key as well as you have the exams. I'll put the answer key on Canvas so you can kind of go through. If for whatever reason you have any issues with the grading, please reach out and let me know. But I try to go over them pretty detailed and then slow there. So that's kind of where we're at in terms of the class, just kind of housekeeping stuff before we jump into material. Are there any questions from you before you go on? I think I mentioned the announcement, and now I forget exactly. I have to look back. They get kind of like a small curve, it's just a couple points just to get the average up a little bit. I think the average ended up being 76.5 after the curve, so we bumped it up a little bit past 75. I usually like to kind of see those averages, those means, the medians being right around 75. This is a little bit lower than that, so I added a couple points to kind of everybody's grading and the curve that a little bit. Okay. Any questions? Okay, so for those who came in a little bit late, I'll kind of give you your exams back at the end of class. One thing you'll see pop up after today's class is a Connect assignment. So as you start working with your material, start chipping away at that, and working on the problems that are in the sequence in which we're going to cover things. And then probably next week, maybe after Monday's class, for sure by Wednesday, the next Excel assignment will be up because we'll cover enough stuff in Excel in class to be able to start working on that. Okay. So we left off talking about discrete random variables, right? So we were seeing a certain number of successes. We're now going to look at is continuous random variables. So a lot of this stuff at the beginning of class is going to be reviewed today, right? And we're just kind of setting this up a little bit different. So we talked about just regular continuous variables. This is where we can see any response, right? So continuous random variable is just something where we are running an experiment. We don't know the outcome yet, but we know that the response could be any decimal value, right? So we can see the integers, but we could also see anything in between. Okay? So annual income, interest rates on loans, pretty popular examples of this. So any continuous distribution, kind of similar to the discrete random variables we're looking at with the binomial and Poisson, have these probability mass or these probability density functions. Okay? So this probability density function is going to tell us, like with discrete, it holds the probability of a certain outcome, right? Two responses, the probability of two successes, the probability of three successes, so on and so forth. The issue is when we're dealing with a truly continuous distribution, and I'll draw it out like this because today we'll talk about a uniform, but for really up until the next exam, we'll kind of be talking about the normal distribution. So normal distribution looks like this. We'll go into more detail later today. But the idea is that I can no longer find the probability of any one value. Because even if you tell me that the lowest value I could see is 0, highest is 100, if I can see any decimal in between there, how many values are in between 0 and 100? If I can see any decimal, how many values are in between 0 and 1? An infinite number, right? So the idea is if I have an infinite number, even if we had a truly continuous uniform distribution, which we'll talk about in a second, kind of 1 over the total number of observations, 1 over infinity, which in the limit approaches 0. So we get this really weird counterintuitive result that if I want to find the probability at any one point, that probability is actually 0. There's an infinite number of possible values, so the probability of any one value is going to be 0. Now, like I said, that's a little counterintuitive because we typically think about things as like, I'm going to see these certain number of responses, but truly it would be an infinite number of possible responses we could see. So what we're going to be able to do instead is find the probability over a certain interval, right? So even though the probability of any one value is 0, if I want the probability of seeing something within a certain range, right, I can find that area underneath my curve, right? So this is just a function. You got to go back to like calculus, and won't make you do calculus here. All right, really what you would want to do in practice is integrate whatever function this is between these two values, right? Find that area under the curve. We're going to be able to kind of sidestep that integration in this class and make life a little bit easier. But that's the idea behind what we're doing. So I can find the probability over certain intervals. Once I do that, I can kind of graph them like I have here. You know, in practice, it might look something a little bit more like this, where I think they do this in calculus. I always thought this kind of helped, right? Even if I made these intervals like really small, and I found like all these little rectangles, I could kind of graph them just like I was my discrete variables, and I could kind of get this nice continuous distribution. And I just made those rectangles kind of skinnier and skinnier. So we're going to have a function that tells us the probability over these certain intervals. And we'll look at a really easy one today, and then we'll look at a little bit more complicated one towards the end of the class. But then say we can kind of sidestep this. So our probability density functions are giving us probabilities over certain intervals. So I'm thinking about kind of some of the properties. It looks everything we've talked about. All right. So I can't see, for any interval, when I'm looking over this probability density function, I have to see a value of 0 or greater. Right. The very lowest the probability could be a 0, but more than likely it's going to be something positive. Even if it's close to 0, it's going to be a positive. Right. So we have greater than or equal to 0 there. If I were to integrate over the entire range of values for x, this function, right? Or essentially, if I'm integrating from negative to positive infinity, I'm finding the area under the curve. It's almost like I've taken all these small little rectangles, right? Added up the probability of every possible interval that I could ever see. So it's kind of like when I took every possible outcome with a discrete random variable, when I added up all those probabilities, we said they have to add up to 1. So same kind of idea here. If I integrate this function over the entire space, or I can think about it as creating all these really like infinitesimally small rectangles, they should add up to 1. That's all that point 3 is saying here. And then point 1, we're going to try to trick you this or anything, but we can't see any jumps. So I couldn't see my function do something like this, right? Where it's like a kind of jump up, right? It's got to be this nice, smooth, continuous line. Like I said, we'll basically just be dealing with the normal distribution in this class, so we don't have to worry too much about that. So very, very similar to kind of what we did with that discrete random variable. It just mathematically looks a little bit differently. But really all you have to remember is this visual, which is the area under the curve is 1. That's all we're saying. Right? So this, just like before when we were doing Venn diagrams, and we said the entire experimental outcome space, or this rectangle, was 1. Well, now our experimental outcome space is just the area under the curve, right? I can see this x variable take on values somewhere in this range. Okay. So the probability underneath, we see something that's from negative to positive infinity is going to be 1, right? We're guaranteed to see something within that range. So instead of dealing with this normal distribution, we'll start out with an easier one, which is this uniform distribution. Okay? So uniform distribution so it's this really unique situation where every interval of the same length is equally as likely. So if we start to think about what that looks like, I'm going to think about my y-axis as kind of representing some level of probability. So let's say I want to know what's the probability I'm in between 0 and 1, and somehow I'm able to find that and I graph it. All right. So I've got the probability of this interval of 1, right? 0 to 1, this is 1, is some amount here, right? So maybe just to give it a value, maybe it's 0. And then I could think about, okay, well, if I had another equally sized interval, right, going from 1 to 2, the interval length there would be 1. It has the exact same probability as this other interval of space 1. And then the next interval of space 1 has the exact same probability, right? And I continue to do this up to, I don't know, I'll do 9 here, because I think I made this 0.1. You can kind of think about it as here, I've got 1, 2, 3, actually I need to go all the way up to, sorry, 10 here, right? So I would have 10 equally sized intervals, right? Where the probability of each one would be 1 over 10. Now, it's not always nice and easy where we start at 0 and end at 10 for these uniformly distributed variables. Maybe I can only see it take on values in between 33.5 and 72.19, right? So it's a little bit harder to figure out what this probability is, but we have a probability density function that will tell us that. But the real idea with this uniform distribution is you're going to have this minimum and maximum value that you could see this variable x take on, right? Any equally sized width interval has the exact same probability. So instead of a curve, our curve now is essentially a horizontal line. So what we're going to end up kind of using the notation, and I know I'm going to change this before the exam. I used to use this with kind of D and C here. And that's how I'll show you things today. But I'll kind of give you the formula every single time in terms of the minimum and maximum as well, right? So C is just the minimum, D is just the maximum of this uniformly distributed variable. So the way that we find this probability or the height of our uniform distribution, well, here I said it was 1 over 10. It was easy to think about there because I could break from 0 to 10, I could break it down into 10 intervals of space 1. But more generally, right, you can kind of think about this as if I have 2 possible outcomes, like flipping a coin, you said the probability was 1 over 2. We have the dice, 1 over 6. And in general, we were saying kind of 1 over n. We had that classical method, right? That's the same idea. Everything's equally as likely. It's just now I can break this down into not just like 6 outcomes, but, you know, an interval of width 0.2. Right. So what's the height here? We're just going to actually do 1 over D minus C, or said differently, 1 over the maximum minus the minimum. Or that's another word for it. You remember what we said? The maximum minus the minimum was 1 over the range of possible values. That's all we're doing. So we can always find the height of this uniform distribution, and we always are going to have to be told the lowest and the highest possible value. So from here, we can start to think about what's that probability density function. It's actually going to be this function right here. So if I want to be the probability of being in between any 2 values, I'll show you visually what A and B look like here on the board. A and B just represent the values that I'm interested in, kind of where my interval starts and stops. So maybe I have the same sort of thing where I've got this uniformly distributed variable from 0 to 10, which I use that with the range equation, or 1 over D minus C, to find the height. Let's say I was interested in finding the probability that I'm in between 5.5 and 7. So here's my maximum, my minimum. Here's where my interval starts and stops. That's all A and B is referencing, the 2 values where my interval starts and stops. So I could just plug values into this density function and it will spit out at me the probability that I'm in between these 2 values. Now, an easier way to do this, you'll notice this is just a rectangle. I'm always going to know the height of my rectangle, which is 1 over 10 here, times the width of my rectangle when I'm going from 7, sorry, to 5.5, which is 2.5, right? So 2.5 over 10 would spit out at me that probability of 0.25. Now, more generally, what was I doing there? I was taking the height of my rectangle, 1 over the maximum minus the minimum, or 1 over D minus C. And then I was just multiplying that by the length of my interval, which how could I find that? I was just subtracting A from B. Anytime I multiply by 1 over something, it's the same as dividing it. So I could actually rewrite this is that density function I had up there. But in practice, I think it's probably just easier to think about for finding the height of your uniform distribution using that 1 over the range equation. And then once I have the height of the rectangle, it's pretty easy to think about what the width of my interval is. Height times width gives me the area of a rectangle. All right. Or like I said, you got that formula in front of you, you want to plug everything in there, that's fine too. I just think the visual and being able to draw this out as a rectangle always just helps make a little bit more sense. So let's put some actual numbers to this. I think I have a nice visual here. Oh, I just gonna have what our entire uniform distribution looks like. So before we go to some problems, there's one other thing that I wanted to tell you about the uniform distribution. So let's use this example where I've got 0 to 10. I think it's fairly intuitive here. But if my interval goes from 0 to 10, what do you think, if you had to guess, what's the mean of that distribution? So if every value is equal as likely, think about the mean is going to be this middle point of the data. Okay? If I can see any value from 0 to 10, they're all equally as likely, my mean would be what? Yeah, just whatever splits this distribution in half. In fact, the normal distribution and the uniform distribution, the first two continuous distributions we'll talk about, are always symmetric. So that mean is also the median. It's exactly in the middle of the data. Okay, so in this case, everything's equally as likely on either side, so it's just the middle value. So really what was I doing there? I was taking the maximum plus the minimum dividing by 2. I was finding the average of 2 numbers or the mean of 2 numbers. That's all I'm doing there. So that's pretty intuitive. Now the variance is not intuitive. It's just always going to be this equation. Right? The reason why is you could walk through if you really wanted to and think about, what would you be doing? You'd be taking the sum of all these x values minus the mean, but the mean is equal to that. You're squaring those deviations, but then you're also multiplying by the probability density function, which was what? D minus A over D minus C. And you can use some really fancy mathematical proofs, and you walk through it line by line, and you end up with a bunch of things canceling, and you're always going to get that. Your variance is just the range of your data, right? The maximum minus the minimum squared divided by 12. Like I said, that's not an intuitive result. It's not easy to see that unless you really want to walk through the mathematical proof, which I'm not going to waste time in the class if you're really interested. I said, I know there's links to this, you can kind of walk through it if you like this. So we've got some nice equations. Always know we can calculate the mean and variance of our uniform distribution and our standard deviation, just like before. One added step, take the square root of the variance. It's all we're doing. Okay. So we'll work through a couple examples here and think about this. So I've got kind of this old movie, which this is an actual movie. If you guys ever want to see like a great early 90s, late 80s hair walk. Such a bad movie, it's actually funny and good. But let's say they're coming out with a second one and it's movie theater and they're trying to predict how much popcorn they need to make, right? So kind of this toy example. But what if I wanted to find that mean pounds of popcorn demand, right? So I've got no longer a uniform distribution that's in between 0 and 10, but I have that I know demand is going to be uniformly distributed somewhere between 1 and 10, right? So I'll give you a little bit of time. Hopefully this is an easy one. This is kind of making sure people are just paying attention to what I was saying earlier. So this mean is this pretty intuitive result. Kind of discussed how we do it up here on the board. Kind of having the equation written out in terms of D and C for the maximum and the minimum. What if I wanted to find the mean for this uniform distributed variable that goes from 1 to 0? Okay. Be a little bit of time working this. Not talk about it. All right, not giving you too much time on this one. So if you didn't get an answer in, make sure you get your answer in now. I think I counted 17, so everybody make sure they get something in here. I'm gonna close it out. All right. So which of these makes absolutely no sense in the context of this example? 95, right? The mean has to be somewhere in between my minimum and maximum value. So right away I can rule that out. From there, all I'm doing is finding the middle value of my minimum and my maximum. Now my minimum is now, forgot my marker, but 1, right? So if we're thinking about, I guess I can do it over here. My minimum is now 1, my maximum is still 10. So I'm looking for that middle value. 10 plus 1 divided by 2, that's the mean of those two numbers. I should get that mean of 5.5. Okay. Questions on that one? Just finding the mean of the minimum and the maximum. Right? So you're just adding those numbers up and dividing by 2. Okay. So hopefully, by the time we get to the second exam, when I ask the question like this, this would be really easy points. Right? What's a little bit more difficult, right, is if I want to find the probability I'm in between two values. So just as a reminder, we said here's that density function, or what I would suggest, draw out what your uniform distribution looks like, draw out what interval you're looking for, and then think about it as the area of a rectangle, where the height of your distribution was what? 1 over the maximum minus the minimum. Okay. So got kind of a similar setup here. If the movie theater makes 9.5 pounds, what's the probability? Popcorn. What's the probability demand is greater than that, right? Or that they didn't make enough. So basically, what's the probability that demand is somewhere in between 9.5 and that maximum of 10, right? So I'll give you a little bit of time to kind of work on this one. I want to get the responses so I can kind of see how we're thinking about this. Give you a minute and a half, 2 minutes, and we'll kind of talk about this one. Talk to people around you. Maybe they know something you don't know. You might know something they don't know. So demand can be anywhere between 1 and 10, and you're wanting to find the probability that it's somewhere in between 9.5 and 10. Or I said probability. You want to find percentage form. So once you find your probability, you'll have to move the decimal 2 places. All right. If you haven't gotten an answer in, take your best guess here and then we'll talk about it. We had 16 people. All right, there we go. We close it out. So, like I said, let's draw the visual out. So it starts at 1, stops at 10, right? That's my minimum and my max. Or if you think about this as C. To find the height of my uniform distribution, I said it's always just 1 over the range. So here, that should be what? Yeah, 1 over 9. What you wanted to find is the probability that demand is somewhere in between 9.5 and 10. So if I think about this as a geometry, the easiest kind of way to find the area of a rectangle, I'm just going to take the height of my distribution, multiply that by distribution. Height of my distribution, or the height of my rectangle, multiply it by the width of my rectangle. What would the width of my rectangle be here? 0.5, right? So it should be what? 1/18 or 5.6%, right? 0.056 is a probability. Now I could have plugged everything in here, right? So my A and B is kind of a weird situation where, well, I know the maximum value. So if I say what's the probability demand is greater than 9.5, I already kind of told you it has to stop at 10. So I could plug my values in here for my beginning and end of the interval I was interested in, my A and B values. I could then plug in my maximum and my minimum. If I go ahead and get all that entered in my calculator, I'll get the exact same thing I did up here. Okay. Any questions on that before we keep moving? Shouldn't be too bad, hopefully. So you kind of have what I did up on the board here, just on this slide. I've got this last one to make a point, but take it easy on you. Think about not making you guys work through this one. So, what if I ask, what's the probability that they make 9.5 pounds of popcorn, that it's exactly equal to what demand ends up being? So I want to know what's the probability that it's exactly correct, or what's the probability that the demand is not between 9.5 and 10, but it's exactly 9.5. That probability could be, I said it earlier when I was just talking about continuous distributions in general. It's this really weird counterintuitive result. The probability of any one value is that if there's an infinite number of possible decimal answers, the probability of any one of those answers being the outcome is just 0. So we can actually prove this to ourselves using that density function. So think about if I have this uniformly distributed variable, and I want to know what's the probability it's exactly 9.5. So here's my C and D, or my minimum and maximum. So I can kind of think about, I'll plug in that into that density function I had written over there in my denominator. Where does my interval start and stop? At the exact same value. So here I've got 9.5 and 9.5. Anytime I'm looking for the probability of any one value, the numerator is always going to be 0. So with our uniform distribution, it's kind of this nice, I guess, support for what I'm telling you. I guess you're kind of taking me at my word, but the probability of any one value is 0. Well, at least here in the uniform distribution, we can see that if we use that density function, sure enough, that plays out. Okay. Questions on that before we keep moving? So that's kind of the uniform distribution, this really unique situation. We see it pop up every once in a while. What we're probably more focused on is going to be the normal distribution. So before I get to talking about that a little bit, I just want to think about cumulative densities and kind of relate this to a little bit of stuff we've already talked about. I think some of what we'll do the rest of today and then kind of next week, this will help it make a little more sense. So let's say I was writing things out using a cumulative density function. So what we said when we were doing this for the binomial and the Poisson, if I make something cumulative, it says start at this value and add up the probabilities of every value below this, right? Well, that meant we had to use the binomial equation a bunch of different times and add them up. Well, with a continuous distribution, really all we're saying with a cumulative density function is if I take a certain value, let's call it A, and I want to know the cumulative probability of A, what that's really saying is, what's the probability that I see this random variable X take on the value of A or anything less than that? That's all my cumulative density function means. Right, so I plug in this value of A, my cumulative density function tells me the probability I see that value of A or anything less than that. So And kind of think about it, as my values for x get higher and higher, that cumulative density function is going to get closer and closer to 1, right? Because the entire area of the curve is 1. If A is way out here and I shade in this entire area, right, I'm going to get really close to 1. If I have really low values of A, well, then the probability of seeing something that's below that is going to be really, really small, or my probability is closer to 0. If income was like normally distributed, you can kind of think about, well, what's the probability that if I select somebody at random, they make less than $5,000? Well, not very high, right? What's the probability that they make less than, I don't know, $200,000? That's most people, right? I mean, there's some people on the other end, but that's a pretty high probability. So that's the idea of this cumulative density function. So that's what I kind of had up on the board here. We can think about the cumulative density function for A is just telling us the probability we see A or anything below that. And we're going to write that using kind of capital F of A, right? Just to kind of give it a name. So what if I wanted the probability of seeing something greater than the value of B? Well, if I use that cumulative density function and I plug B into it, that's going to tell me what? The probability I see B or anything less than that, right? So if I'm using that cumulative density function and I plug in B, it's going to tell me the area to the left. But if I want the probability being greater than B, just like on the slide, I actually wanted the area to the right, so I can use our complement rule. If I know the area to the left of B, the area to the right of it must just be 1 minus that. Right? So it's not like we'll like call the complement rule over time, but it's kind of hiding behind the scenes, right? We know that, when I run this experiment, I can only see one value. So if I'm thinking about the probability being less than or equal to B, and the probability being greater than B is just 1 minus that, right? Those have to be complementary events. What if I wanted the probability of being in between two values? Okay. So this gets a little bit trickier. But if I wanted to find the probability of being in between two values, how can I use that cumulative density function to find that?
Would you find the cumulative density of A and then the whatever the complement of the cumulative density of B?
Would I simply add them up? So let's think about what I would be doing. If I use that cumulative density function for these two values, what I actually want is the probability I'm in between A and B. The cumulative density function tells me the probability being less than these values. So if I've got this red area, and I've got this black area, how can I find where I only have it, right, where they don't overlap?
Subtract.
Yeah, just subtract this smaller area from the larger area, and I'm left with just what's in between. So what that really is saying is, take that cumulative density function for the higher value, subtract the cumulative density function for the lower value.
That's if you know what's on the left and right of A and B. Like in the non-shaded areas on the screen, you know both of those?
So I could use, once we have an actual function, I could find the probability of being less than A. I could then use that cumulative density function to find the probability of being less than B. Did I say A the first time? Probably being less than A, and then use it again to find the probability being less than B. Then subtract that smaller area from the larger area, and all I've left with is what's in between here. Kind of can think about it this way. These are cumulative, right? So if I put some actual values to this, let's say I had 10 and 5 here. This is really saying, okay, what's the probability X is less than or equal to 5? Sorry, less than or equal to 10, minus the probability that it's less than or equal to 5. So really all this is telling me is the probability that I see X be greater than 5 or less than or equal to 10. Right, that's why that process works. Because the larger values cumulative density function includes the outcomes that are in the smaller values cumulative density function as well, right? Because it's always looking to the left. Does that kind of, yeah. Any other questions on that before we keep going? All right. think this one's not too interesting, but right? Maybe if I want the probability to see something below A or greater than B, well, I can use the same process I just did to find the probability that I'm in between these two values, and then just subtract it from one. So once we start working with some of these, we'll see like a lot of this becomes like, maybe I find an area and like I can break down the area under the curve into pieces. Here I could break it down into these two tails and then kind of this middle part in between those two values as well. So if I can use that cumulative density function to find the probability I'm in between A and B, if I subtract from one, that's the probability I'm outside of that range of values. Or in this example, right, the probability that I'd be less than 5, but greater than 10. So we'll start putting more numbers to this and actual functions when we start dealing with the normal distribution. Well, these are some of the principles that we're going to use. Let me think if I want. I'll hold up on something, but hopefully I remember to do it when we get to our other material here. So now we're going to kind of actually start working with this normal distribution. So one thing that I'll put up on Canvas, and we might take a look at it today, but I'll expect that you kind of have it moving forward. So when we meet again on Monday, kind of from here on out, maybe printing it out or being able to pull it up on your computer or phone when you're in class. I'll be posting something on Canvas called a standard normal table or a Z table, right? So I'll kind of mention that before we leave class again today and kind of we'll take a look at it. But that's something that you'll need to kind of print out to have if we're doing some of the IQ questions in class. And also it's just easier for you to see. You'll see once I pull it up, like the numbers are going to be very small to you. And it's hard for me to kind of zoom in and be too productive. So having those in front of you will be helpful. So where does this normal distribution come from? So there's this guy, super smart. His last name was Gauss. So the normal distribution is sometimes called the bell curve, right? Kind of drawing it out, looks like a bell, right? Or sometimes called the Gaussian distribution, right? This is the guy that came up with it. Now allows us to do some really cool things once we get a better understanding of it, building confidence intervals, doing some linear regression. Supposedly, like this guy was, a genius just to kind of set up how to come up with it or to discover the normal distribution. So apparently, the legend goes when he was a kid, he was misbehaving. Teacher turned to the corner, said, "Start adding the numbers up from 1 to 100." Thinks he's going to be there a while, right? 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, all the way up to 100. Comes back in a matter of seconds and has the correct answer, right? So just kind of an interesting mathematical thing to think about. If I'm adding the numbers up from 1 to 100, what's 1 plus 100? 101. What's 2 plus 99? 101. What's 3 plus 98? 101. All the way down to 50 plus 51 is 101. So I've got 50 pairs. They're 101. Just multiply those two. Now I get 5,050. Right? There, somewhere. Right? 5,050. So even at a young age, there's an actual formula where you can do this. Basically, his brain is able to just one of these freaks, that can visualize math and think through it in their head, right? You don't have to write anything down. But basically, him and others did a bunch of work and a bunch of integration that we're not going to have to, right? So we'll first start thinking about this normal distribution and some of its properties, right? Before we can actually start using it. So we see it pop up a lot in nature. This is why it's really relevant. So human height, rainfall, human weight, temperature, really a lot of different biological markers. So human performance and any type of physical endeavor, eyesight ability, all these weird biological things. Typically there's a normal distribution, right? Most people are kind of in the middle. Some people have really, really high values. Some people have really, really low values, but the majority of people are kind of in the middle of that distribution. So we see it pop up in nature a lot, which is kind of what how it was discovered and what the book kind of talks about if we go back far enough. And then I already mentioned we'll eventually be able to use it to do some cool stuff with linear regression. So here's the probability mass function. Don't write this down. I'm never going to make you use this, right? But I'm showing it to you just so we can get an idea about a couple of things. So here's that density function, the density function that we had for the uniform distribution, which is B minus A over D minus C. This is the density function for our normal distribution. So just a couple things to point out that are kind of interesting. So we've got all these different things in here. We end up seeing pi and that natural number e. So kind of interesting that these two very unique mathematical numbers both pop up in the normal distribution, which, like I said, you could probably YouTube spiral this, I don't know, look into like golden ratio and things like that. And just how much pi and kind of just e pop up in nature, and they both happen to pop up in the normal distribution. But the only other two components that we really have, right, we're looking at different values for x. Well, that's just thinking about, probability. I see, human height be below 60 inches, or something like that. So this is just going to be values that we're plugging in that we're interested in, finding the probability of being below. But the only other things that really define this distribution are going to be the mean and the variance, right? They both pop up there, right? So we can have all types of normal distributions, right? Rainfall and human height are both measured in inches. They're both normally distributed, but they have very different means, right? The mean rainfall is, I don't know, 3-4 inches maybe a month at most. I think, I forget what I've got the data. We'll start looking at it a little bit next week. Human height is like, above 60, right? So we have different means, but they're both normally distributed. So we can start to think about some other characteristics. And I already mentioned one of them, which is that it's symmetric. So the mean is equal to the median is equal to the mode, or we can think about it, if we find the mean of a normal distribution, it should exactly split it in half, right? So if I've got this normal distribution and I'm thinking about the mean, the probability of seeing something above and below the mean should be 0.5, right? Because the mean is the same as the median if it's symmetric. I already mentioned what we can kind of gather from that probability density function is it's also defined by its mean and its variance. So we can think about how are the mean and the variance going to influence what this normal distribution looks like. So it's always going to kind of look like a bell curve, but the shape of that bell curve might change, right? So if I'm plotting on the same graph, right? And I think I make this point later, but I'll kind of leave it here. Let's say I've got normally distributed female height, right? And then I think about, I want to, on the same graph, right? So I'm thinking about my variable's height here, put the distribution of male height. What's that going to do to my distribution? If I think about, I want to plot male height relative to female height, where should this distribution be? Kind of the center of it. Well, if we look at data, the average male height is higher than the average female height. But if it's also normally distributed, then it should be that normal distribution is symmetric around that mean. Right? So the mean of my normal distribution is just going to shift it along the x-axis, right? That's all that's going to do, right? So it tells us kind of where that's going to be. Now, one thing to kind of point out here, when we start thinking about distributions, when we graph them relative to each other, yeah, the average is higher, right? But there's still pretty significant overlap in these two variables. So, it's, for any one observation, right, I might see male height be somewhere down here. And for any one observation from the female data set, I might see female height be up here, right? Even though the average male height is greater than the average female, if I'm looking at any two individuals, right? I could have females that are taller than males. I could have really tall males, really short females, vice versa, right? But kind of now that we can start graphing these, we can start thinking about these different groups relative to each other, whether or not this is here, I broke it down by gender, but you can do things by country or, by company, whatever you do. So we've got that this mean is going to shift our distribution left or right on that x-axis. The higher the mean, more to the right, lower the mean, more to the left. The variance is also going to tell us something about the distribution, which is the spread of the distribution. So trying to give you a visual, and I've got one on the slide, but I think if I do some things on the board, it might make a little bit more sense before we get there. So let's say I've got two distributions that are both normally distributed, but they have exactly the same mean. But let's say, so the mean of these two are the same, but the variance of that second group, right, much, much higher, right? So the greater my variance, what does that tell me about the possible outcome? So just like with kind of same thing with data, what would it tell me about a data set that if I had a higher variance?
Variety.
Yeah, it's more spread out, or there's more variety in the values that I'm seeing. So another way to think about this when we're thinking about something that hasn't happened yet is that all the possible outcomes I can see, there's just more variation in those outcomes, right? So if there's more variation in the outcomes, that means that I'm less likely to see values that are close to the mean, right? Because remember, when values were close to the mean, I subtracted the mean and squared it, was adding a very small amount to the variance. But I have a high variance now. So that must mean that when I'm looking at some of these values and I'm subtracting the mean, then I'm getting kind of really large gaps from that mean, or that values further from the mean are becoming more likely. So I'm thinking about what the shape of this distribution is going to look like. Having a higher variance kind of flattens my distribution, right? Or said differently, having a lower variance kind of creates a higher or a more peaked distribution. So what to think about is like the mean shifts it along the x-axis, and this isn't really a shift on the y-axis, but it's like when the variance changes, it pulls that distribution up higher. If I've got a very low variance, kind of flattens it out or pushes it to be kind of closer to that x-axis line as I get a higher and higher variance. So I think I've got another one here. You could put multiple values on here if you wanted to. And, as I get a higher and higher variance, I'm kind of getting this flatter and flatter distribution. But the reason why it's flatter is the higher variance is really just telling me, oh yeah, that means that you're not going to see values near the mean near as often, or the probability falls of seeing those values. And it's going to be way more likely you see values that are far from the mean. So those probabilities are going up. Question here. No. So I had this was from actual survey data. What can I gather if I look at these two distributions? So the one that's kind of easier to think about is which of these male or females, or men or women, have a higher mean? Well, if I'm looking at the middle part of these normal distributions, the average female height looks like it's going to be around 64, 65. Average male height looks like it's going to be around 70. I don't know, 72, 73, maybe a little bit less. So that kind of tells me that second group males is a slightly higher average. But which of these has a higher variance? Yeah, so we said a higher variance means that the distribution is going to be flatter. So which of these is kind of shorter or flatter? The male distribution of height, right? In fact, most things, if we look at biological measures, males just tend to have higher variation in their biological outcomes, I guess. Right? So we get much higher variance. We've got some pretty cool things that we can start doing with the normal distribution. Right? So now that we know it's defined by its mean, defined by its variance, we can start to think about, and I don't think I'll get to prove to you why this is what it is today, but I can at least tell you, and then next Monday maybe we'll kind of solidify why this is the way it is. So if I were to go one standard deviation above and below the mean for a normally distributed variable, that probability will always be somewhere in, that probability being in between these two values will always be about 68%. So no matter what normally distributed variable I'm looking at, if I go one standard deviation above or one standard deviation below the mean, well, then if I'm choosing an observation at random, the probability it's somewhere within these range of values is always going to be 68%, or probably 0.68. So this would be like saying something like, I don't know, let's say the mean height of males, it's 5'10", so let's say it's like 70 inches. Let's just say, for the sake of this example, the standard deviation is 5, right? If I were to say, okay, what's the probability that I'm in between, if I choose a person at random, that they're in between 65 and 75 inches of height? Well, that's one standard deviation below, one standard deviation above. That probability should be 0.68 or 0.683, right? As long as we know it's a normally distributed variable. So like I said, we won't probably get to prove why this is what it is today, but we'll at least start the discussion. And then if I go 2 standard deviations out, what do you think probably happens to that probability? It should, yeah, if I go 2 standard deviations out, that would be what, 80 and 60? Well, now I'm just looking at a larger area under the curve, that probability should be higher, right? So if I go 2 standard deviations above and below the mean, I get that the probability of selecting an observation at random, it's somewhere in between 2 standard deviations above and below the mean. It's already as high as 95%, or probably 0.95. And then I can go 3 standard deviations, and I'm basically at 1, right? So when we start thinking about different values for these random variables and how many standard deviations away from the mean they are, anything over 2 is pretty far away, right? I mean, if we go 2 standard deviations above and below, we're kind of getting a pretty good guarantee that if we selected someone or an observation at random, depending on the example, that we're getting a value somewhere in between 2 standard deviations above and below. In fact, we go to 3 standard deviations, it's almost a sure thing, right? 99.7%. So I don't know what other classes many of you have had, but have you guys ever heard of, or has any of your professors mentioned 6 sigma? You heard about this? So this is kind of the idea. It stems from sigma is our standard deviation. So if I am at 3 sigma above and below the mean, I'm at 99.7%. If I can go 6 sigma to the left and the right, I'm at 0.999999, right? I'm basically at 1. So I'm guaranteeing that I see something within those ranges. So that's a little bit of a foreshadowing. We'll talk a little bit more about that when we get to sampling, the idea of 6 sigma. So we've got that they're defined by their mean and the variance. So the way that we're going to write this out is that we've got some random variable x. It's normally distributed. Here's its mean. Here's its variance. Now, that's how we're going to write it. What we're going to want to do in order to use the work that other people have done is turn a normally distributed variable or transform a normally distributed variable into what we would call a standard normally distributed variable. Okay. So the standard normal distribution, right, is going to have 2 special qualities. Right? The variance is going to be 1 and the mean is going to be 0. Okay. So why is that useful for us to think about? Well, if we've got a standard normal distribution, and I think I'm jumping the gun a little bit here, but when we know it's a standard normal distribution, we end up calling it Z, just to kind of differentiate that from any other randomly kind of just regular normally distributed variable. So if the variance is, or sorry, if the mean is 0 and the variance is 1, what's the standard deviation? Should just be the square root of the variance. So the square root of 1 is 1, right? So we have this really nice, unique property. So our standard deviation is 1. So then when I'm looking at different values for Z, I'm looking at the value, let's say Z is equal to 1. How many standard deviations away from the mean is this value? Well, if the standard deviation is 1, this is 1 standard deviation away from the mean. And if I saw, I don't know, Z was -2, that would tell me that it's 2 standard deviations below the mean. Right? So if I can convert my normally distributed variable into a standard normally distributed variable, I get these really nice, clean interpretations from these Z-scores, right? Or these values from a standard normal distribution. Also, you can imagine if I go back to that probability density function and I plug in, I'll open the screen here. There we go. If I plug in 1 and 0 here, this simplifies, becomes a lot easier to integrate, which is why people have already done that, and then we can use their work. So skip ahead here, get back to what I was talking about, right? The standard normal distribution. And we can kind of think about, I already mentioned this, right? Different values for Z are going to represent the number of standard deviations away we are from the mean. Positive values mean we're going to be above the mean. Negative Z values, we're going to mean we're below the mean. Okay? So we start out with a normally distributed variable. we can't really use that standard normal or that Z table until we convert our normal distribution into a standard normal distribution. So what we can think about the visual here is I've got some normally distributed variable X. It has some non-zero mean and some non-one variance or standard deviation, right? It's not standard normally distributed. I might then be interested in what's the probability that I see a certain value or less. Well, if I convert these into z-scores, right? If z-scores or these z-values we said are standard normally distributed, then I know my mean should just have a z-value of 0, because the mean is 0, standard deviation going from the mean. And I would convert that value of A into, well, how many standard deviations, in this case, below the mean is this value of A? So how can I turn this value of A, maybe this is like, what's the probability someone is 64 inches or less? I got to turn that 64 into a z-value, or the number of standard deviations away that I am from the mean. So the way we're going to do that is simply subtract the mean from that value and then divide by the standard deviation. Okay, so it's going to represent these z-values are the number of standard deviations away we are from the mean once we've converted these normal distributions into these standard normal distributions. But I want to give a little bit of insight as to why this process works, so or at least just prove to you that it works. That's maybe just for the sake of easing it. I might just do this in Excel. I think it'll make it a little bit easier to see, and I also I'm guaranteed not to make a math error in my head. So here we go. I can kind of show you with some more interesting values. So just to prove to you kind of what this is doing here. Let's say I start out with a really small data set, something like this, right? And we'll call this our original variable X, and it's normally distributed. It's symmetric around the mean, okay? So if I wanted to find the mean of X, and then I'm going to find the standard deviation of X, okay? Maybe. There we go. So I use my average function, or I add these values up, divide by 5, I get a mean of 6, right? I could then do my standard deviation. I'm going to treat this like it's population data for the sake of what we're doing here. And I get, well, that's not a very nice standard deviation. So what do I want here? Well, I guess it doesn't matter, right? I can show you that, in Excel for sure, we can deal with any values, right? So I have this non-zero mean and this variance that's not 1, right? So I'm going to go down here and I'm going to create this new value or this new variable z. And what I'm going to do is first just subtract the mean, okay? So for each one of these, I'm going to take the X value and I'm going to subtract the mean of that X value or that X variable. Now, I want to be able to copy this down. I've only got 5 observations here though. So to kind of match up with what we would do by hand, right? I'm just taking the next value of 4, subtracting that mean. Next value of 6, subtracting mean. Nope, I accidentally hit a negative sign. There we go. Take the next value of 8, subtract that mean. Take the next value of 10, subtract the mean. Okay. So here I've got my new variable z. Well, I at least have done the numerator, right? So by subtracting the mean from everything, when I find the mean of this new variable I created, oops, sorry. So you can see this. Notice I get a new mean of 0. So by subtracting that mean, I guarantee that my new values will be centered at 0. Now, the other part of that z-score equation was that I divide everything by the standard deviation. So here, I'm not going to go in and type it. Well, I can actually go. So I'll divide by that standard deviation I have right here. Okay. So I'm dividing by that standard deviation. And I probably could have froze some of these cells so that when I copy this down, I always want to use the same, whoops, that's not a dollar sign. I always want to use the same mean and the same variance, right? So I'm just going to copy this down instead of entering it every single time. It'll update to use the next observation each time because I didn't freeze that cell, but it'll always subtract the mean and always divide by my standard deviation, okay? So now when I copy these down, here's my new Z values. Notice my mean is 0 and the standard deviation will be 1. And you could play around with these values as long as you have a symmetric distribution. So let me even show, like, let's do 20, 40, 60, 80, 100. Notice I'm getting these nice kind of clean numbers. Let's do, oh, what's a good one? 40, 45, 50, 55, 60, except for that's not 60, right? Notice I keep getting 0 and 1, right? So I don't know, just kind of, I don't know, maybe it's easier sometimes to prove things to yourself with numbers as opposed to going through the mathematical proof as to why subtracting the mean and dividing by the standard deviation always gives you this standard normally distributed variable, okay? Any questions on that? Now, let me see, I'll save this at the end of, whoops. I'll save this at the end of the class and I'll just put it up on Canvas just in case you want to take a look at it. But the idea here is once I know how to convert these into Z values, I can think about, you have this nice, what's that side? Occasionally steal things from the book and I really like this visual, right? So if I'm looking at values for X, once I turn these into Z values, the Z score or the Z value always tells me the number of standard deviations away the original X value was from the mean. So if I look at something that's 1 standard deviation above the mean, it should have a Z score of 1. 3 standard deviations below the mean, that X value would have a Z score of -3. So why does this work out? Just to give a little bit more insight here as well. So if I've got my equation for converting these X values into Z scores, let's say I'm interested in something that is 2.5 standard deviations above the mean. So that's the X value I'm interested in. It's 2.5 standard deviations above the mean. I'll subtract the mean, divide by the standard deviation, and turn it into a Z score. But notice, the mean minus the mean cancels. Standard deviation divided by the standard deviation cancels. And I find that for an original X value that was 2.5 standard deviations above the mean, I'll get a Z value of 2.5, which is why these Z values always represent the number of standard deviations away from the mean that our original X value was. Any questions on that? Follow this a little bit here. So I'm going through a lot of this and probably doing more than I need to, but I want to kind of set us up to have a really good understanding of the normal, standard normal distribution, because we're going to be using it a lot from here on out. Okay. So what use are these Z's? Why the hell am I going through all this? Right? Why am I converting my normally distributed variable into a standard normal distribution? We've already alluded to the fact that we can use some work that's already been done, but I might want to find the probability of them in between two values. Okay? So other people have done this work. We've got a standard normally distributed table or a Z table, and it kind of allows us to do some things like the following. Okay, so let's say I start out with some X value. Maybe this is, what's the probability that if I chose a person at random, that their height is below 64 inches? I go ahead, I am told, or I can calculate from data, the mean and the variance of height, right? This original normally distributed variable. And I find that the value of 64, it's 1.29 standard deviations below the mean. Okay. Well, what's the probability that I saw an observation that was that many standard deviations below the mean, or anything even further? Right. Well, I can visually think about what that looks like. But if we use that standard normal table, we can look up that Z value or that Z score of negative 1.29, and the table will always give us the cumulative density. Goes all the way back to what I was talking about earlier. So it's always gonna give me that area to the left, or the cumulative density of that Z value I'm looking up. So what does this look like? Here's why I said I want you to print this out, right? This is very hard to see, okay? So I'll put up a PDF, I'll put up some of the files tab, so it won't be any folder, it'll just be sitting there. I think I'll probably call it like standard normal and then parentheses, put a Z table. So let's say I want to look up negative 1.29, right? That's the Z value that I want to find the probability of seeing that or anything below that. The row headings are going to be our first decimal. So negative 2.1, negative 0.4. The column headings are our second decimal. Okay? So we're kind of constrained to only being able to look up Z values that are 2 decimals out. So if I wanted to look up something that was 1.284 standard deviations away from the mean, I'd need like another dimension that had the 3rd decimal and I'd have like a 3D table. That's not very practical, right? So we're going to kind of stuck with this 2-dimensional table. Our first decimal, negative 1.2. Our second decimal was 0.09. We'll go to where those two meet. And this value is the probability I see that Z value or anything below it. Or I see something 1.229 standard deviations below the mean or anything even further below it. And that probability is right around what, 0.1, right? 0.0985. So I can look up any Z value like this. Now, just a couple things to point out. If I look at a Z value of 0, what should the area to the left of that value of 0 always be? Remember, we said the mean of my standard normal distribution is 0. It's symmetric, so it's also the median. So this area should always be 0.5. So anytime I look up a negative Z value, the area to the left of a negative Z value should always be less than, well, if this area is 0.5, any negative Z value is going to be a slightly smaller area, so it's going to have to be less than 0.5. So this is one of those things when we start working through problems, it kind of helps us bound our answer, right? We know that if I look at the negative Z score, it has to have a probability of seeing that or anything below it, less than 0.5. Sure enough, if I look at all these values in the middle here, they're all below 0.5. In fact, when I look at 0.00, that's exactly 0.5. And then anything below that starts to get closer and closer to 0, right? If I go 3.99 standard deviations away, it's not even indistinguishable from 0. Now it's not technically 0, it's like 0.000001, right? But it's so small out to the second, out to what was it, 4 decimals here? It looks like 0. Any questions over how to use that table up to this point? Okay. So if instead I wanted to find the probability that I'm less than 1.29 standard deviations above the mean, with the work that we already did, we actually wouldn't technically need the table. Now we could look it up in the table, and I will after I show this to you to kind of verify, like you can look it up in the table and then find the value. But here, if I want the probability of seeing something that's 1.29 standard deviations above the mean or anything less, from what we did over there, how could I find that probability? Got two things we kind of need to realize. So if this is a symmetric distribution, and the area to the left of negative 1.29 is, what did we say this was? I already forgot. I think it's 0.0985. Can we look it up in the table? If it's symmetric, and if I'm looking at negative 1.29 and this area is 0.0985, what's the area to the right of positive 1.29? Yeah, folds on top of itself. So this is going to be 0.0985. Well, if I know the probability of seeing something above 1.29, how can I then think of it being below 1.29? the complement, or 1 minus that, right? So I know the area under the curve is 1. So this is what, 0.9015. So hopefully, and there's 2 sides of my standard normal distribution of my z-tables. The first side had all the negative values. The other side has all my positive z-scores, right? So all these values should have a probability that are greater than what value? Remember, the mean of 0, the area to the left is 0.5. So if I want the area to the left of positive z values, that's going to be something greater than 0.5. Sure enough, all these values that we look here are all greater than 0.5. So hopefully, when we look at 1.29, we find that 0.015, 1.2, second decimal, 9. Sure enough, we get 0.9015. So sometimes when we do some work and we're doing like multiple problems in a row, we can kind of reuse what we did to make our life a little bit easier. We don't have to go to the table every single time. But now if we just started as a standalone problem, we could also just, go to that table and find an answer. All right. Anything else I want to say here? So one thing I'll kind of mention just to get it out of the way before class on Monday. These are values we'll start to see popping up a lot. And the reason why is because notice these different z values are being this many standard deviations above the mean. The area to the left of the cumulative density starts to get really close. I mean, about 90%, 95, 97.5, 99%. So these are going to be some like benchmark values that we kind of see pop up a lot, especially once we get to confidence intervals and hypothesis testing. Another thing I'll mention, and we kind of already used this, right, over here. But if I ever want to know the probability that I'm above a certain value, the table always tells me the area to the left, or the probability being below that value. So if I ever want to know the probability being above a certain value, I'm going to have to use that complement rule, right? I'll turn my original x value into a z value. I'll look at z value up in the table will tell me the area to the left. But if I want the area to the right, I'm then going to have to do 1 minus that. Right? So that's just kind of, I think, drawing it out. That helps. I think the visual helps there. We already talked about it symmetric around the mean. So the probability being above or below the mean should just be 0.5. And this is the table that we'll kind of want to start using from here on out. So I would ask you a question like this starting on Monday. Right? What's the probability that we see a z value greater than or equal to negative 2.53? We would then use the tables to look up these values, give you a little time to work on it. It's really too hard for me. I've tried to do this before where I show you the question and then show you the table for a while, go back to the question. It's just way easier if you print it out or make sure you have a device that you can pull it up and use that table in class. Now, pull it up on your phone. It's going to be a little bit harder to zoom and navigate. I really would suggest trying to go to the library, wherever, and printing a version of this out and just put it in your folder that you bring to class. Okay. Let me think if there's anything else. So we got a couple minutes. Just kind of some interesting things to point out if you're kind of on your way out. Maybe you'll find it interesting, maybe you won't. So I had a survey data of 12,000 people. You can kind of pull out only males here. And you can kind of see it's like human height really close to a normal distribution. I also found this on Instagram one day. So I don't know what the hell kind of workout it was. There's some CrossFit workout. And they put the results out because I guess people like to compare to each other and where they fit. But when I saw this, I was like, dude, this is pretty wild that when you look at the performance, I mean, the female performance here is, I couldn't draw a normal distribution that looks better than that, right? So you see these biologically, I said the human performance, you see these normal distributions play out all the time. There's a little bit of something goofy going on with male data. But there's probably something about this workout that maybe there was a certain threshold that we saw this little bump. But just kind of seeing this play out, I've got some kind of male, female deadlift stuff I'll use to kind of set up an example to talk about normal distributions next class as well. Other than that, look at that homework, start chipping away those early problems, and I'll see you guys on Monday. Okay.